Recording is on, second half, October 28th. And what we're about to do is try to get a sense for why this proof of coding is a bijection. And the way we're going to do it is we just saw how you do the reverse bijection that takes a proof of code, supposedly an arbitrary list of numbers between 1 and n that's of length n minus 2, and produces a tree via this algorithm. So what I want everybody to do is think hard. Think of a number between 1 and 10, an integer between 1 and 10. Everybody, you got one? Got one? Okay, put it into the chat. One number from each of you. All right, I got a bunch of numbers. Let's see. I'm going to start our randomly chosen proof of code. Code is, all right, C1, C2, C3, C4, C5, C6, C7, C8. What do I got? I got a 3, a 6, a 6, a 9, 3, 1, 5, 4. And that's 8 numbers already. Okay? So let's do it. And let's think about, why does this have to produce a tree for us? And I think if we believe that, then you're probably going to believe that the tree that it produces will have this thing as its proof of code. And then I think it's going to seem reasonably intuitive that it's actually, oh, too late. Yeah, someone was trying to do, let's all do the same number. Yeah, got to be faster than that. But if you believe that it really produces a tree, then I think you'll believe that these two maps are inverses to each other, the coding and the decoding algorithm. Okay, so we build the current leaf list that changes at any moment. And I'm not going to put parentheses, but let's see which numbers are not showing up in our proof of code. 2. I see 3. I see 4. I see 5 and 6. 7. 8 and 10. Is that okay? So please correct me if I make a mistake. Since I don't have this one to check on my own page, then I'm more prone to make a mistake. Okay. So what are we going to do? We'll do this thing in blue again, where we say, all right, 2 and 3 are going to be connected, and I'm going to check, did 3 leave the proof of code? No, it's still there. So I just adjust my proof of code by taking the 3 off the beginning. It still occurs at least once, so it's not on the leaf list, but the leaf list got 1 shorter because 2 got plucked off and no longer exists. Now we quickly try to do this, but not so quickly that I make a mistake. 7's the smallest leaf. It's going to make an edge to 6. 6 is going to leave the proof of code. Excuse me, it's going to leave the beginning of the proof of code, but it's still there at least once, so it didn't enter the leaf list. Leaf list is rather short. It's 8 and 10. Okay, so far. Smallest labeled leaf is 8. It's going to get connected to the first thing in the proof of code, which is a 6. And now I'm a little more careful and I say, aha, proof of code 93154 no longer has a 6 in it. So 6 became a leaf and enters the leaf list. And the leaf list is now 610. And now 6 is the smallest leaf, and it gets connected to the first thing in the proof of code. That's going to be an edge. New proof of code is 3154. The 9 left the proof of code at that moment, so it enters the leaf list, and it's the new smallest leaf. It's going to get connected to, oh, wrong color. It's going to get connected to 3, and 3 goes away from the beginning of the proof of code. And in fact, that was the last time we saw 3 in the proof of code, so it enters the leaf list. And now what's happening? 3 will get connected by an edge to 1. 1 taken off the beginning of the proof of code, and that was its last time to be in the proof of code, so now it's 110. 1 will get connected to 5. 5 left the proofer code entirely, entered the leaf list, and is the smallest leaf. Gets connected to 4. Empty proofer code. 4 entered the leaf list. Joined 10, which is the only other thing on the leaf list. So they are the little edge that's left at the end of the proofer coding, and they get connected to each other. And let's see whether this built a tree. Okay, so what do we got here? We've got an edge from, first edge is 3 to 2. I'm just going to do them in the order that they showed up. Let's see, 6 to 7, 6 to 8, 9 to 6, 3 to 9, 1 to 3, 5 to, what is that, a 1? 4 to 5, and 4 to 10. And yeah, what do I got? Everybody? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it's connected in a tree. So it did recover a tree for us. But let's think about it. Why did this have to recover a tree? Like, you just gave me some random numbers, and you could see when I was writing down these edges one at a time, like I put in the 3, 5 first, excuse me, the 3, 2 first, and then the 6, 7, and the 6, 8. It didn't look like we were building a tree. It looked very disconnected. So there's, first of all, the question, why is this thing connected at all? And it's actually a little tricky when you think about building them up in this order as you go down the process. But it makes more sense if you think about it backwards. So why, let's think about why is the resulting graph connected? And I claim one way that you can think about it is that every vertex, V, has a path to that 410 edge. But when I say the 410 edge, I mean those last two things in the leaf list. And the reason that they all have one is you can prove that by induction reverse induction. How late in the process did they get crossed off the leaf list? So notice every single vertex either is one of those two that is there at the end in the leaf list, or at some point in the process, it gets crossed off. It is the smallest leaf, right? I mean, that's the only way in which these numbers ever get removed from the universe. Either they were there, on the leaf list and they get crossed off, or they start out over in the proofer code, but then there's the last time that they show up in the proofer code, they enter the leaf list and get crossed off, or they might be among these two, but everybody is in this list over here. And I claim if you work backwards in this direction, you can see by induction that they all have a path to these two, right? So of course the 4 and the 10 have a path to each other, right? They're in a little edge. How do I know that the 5 has a path that connects them to the 4 and the 10? Well, when it leaves the leaf list, it gets connected to somebody over here, right? Which was either the 4 or the 10. This one, the 1, how do I know that it has a path from the 1 to the 4 or the 10? Well, at the moment when it gets crossed off the leaf list, it was connected to one of these previous numbers that we already know had a path to the 4 and the 10, and so on. At the stage where I'm worried, does 6 have a path that lets it get to from the 4 to the 10? Well, I know 6 is going to have such a path because at the moment when it got crossed off the leaf list, it had an edge to this 9, and that 9 was among these numbers that still existed at this stage. And they all, by induction, have a path from 4 to 10. So I know that 6 is connected to the 9, and the 9 has a path from 4 to 10. It's a mildly subtle argument, and you have to sort of do your induction carefully. So let me write down a few words, but I'm not going to write down all the words I just said. Using reverse induction on the order in which it was crossed off the leaf list. Does that sound plausible? Think you could reconstruct that argument? Okay, so that's part of it. I'm trying to convince you that this thing is a tree. So it's connected. Now the question is, why is it acyclic, right? Trees are connected forests, connected acyclic graphs, graphs that have no cycle. And so let's ask that question. Why is the resulting graph acyclic, no cycles? And I think that this is also actually easier to think about if you think of building it backwards. First this edge, whoops. First this edge, then this edge, then this edge, then this edge, and so on. If you think about it, when you build it backwards like this, you keep adding on an edge to a vertex that wasn't in your universe. You start out with a universe that has only 4 and 10, and all the other numbers don't exist. They haven't been added at all. Then you add an edge from 4 to 5. Then you add an edge from 5 to, 1. Then you add an edge from 1 to 3, an edge from 3 to 9, an edge from 9 to 6, an edge from 6 to 8. Each time, this new thing, the new vertex that's the beginning of the leaf list, is a vertex that you've never seen before when you're working backwards. And I claim if you build up a graph in that way, such that you're always adding one more edge to a vertex that's never been connected to anybody else, that never existed before, you can't create a cycle. So the claim is you can't create cycles, again, working backwards. In other words, reverse order in which V gets crossed off the leaf list. Because you always add an edge to a new vertex V. By that I mean a vertex that was just sitting out there isolated, that had no edges attached to it. And so you might think, why can't that create a cycle? Well, if you have a cycle in your graph, somewhere there's a cycle. Who knows what the graph looks like? And if this thing, this cycle was labeled, I don't know, 2, 7, 3, 8, 1, 10. Well, the issue is if these edges were added in a way where you were always adding an edge to a new vertex before, the last one that you added in within the cycle was supposed to be new. I don't know, maybe the last one you added in was number 7. But the problem is, right, the 1, the 3, the 2, the 10, and the 8, they were all supposed to be there before. And then you added in the 7. Well, the point is that, yes, how do I want to say this? In fact, am I saying it right? This is a slightly tricky argument. Now it's escaping my head. Excuse me. So, right. So if the, yeah, it can't be, these things can't be added, these 2 edges. If 7 was the last one that was added in this reverse ordering, it can't be have been added to 2 of them. One of them was what created the edge to the 7. It's not that 2 of them did that, because I'm sorry, I'll let you think about it. This is one of these ones that I'm going to stumble over it as I try to say it. Okay. So the point is that it creates a connected acyclic graph no matter what code you wrote down at the beginning. If you do this algorithm that we ran through, and it's not too hard to check once you believe this. Any code produces a tree then it's not too hard to see that that tree, when you do the proof for coding, will correspond to that code. So you can check that these maps are inverse to each other. Okay, so I'm going to regard that as the end of the proof. It's definitely something that's worth pondering. Why does this really work? I'm not claiming that it's obvious at all. I think you have to sit down and convince yourself for a while quietly. But any questions before we move on past the Cayley-Borchert theorem? So I think we're going to get to, in a little while, a different proof of the Cayley-Borchert theorem by very, very different means. But again, something that uses something interesting. All of the proofs of the Cayley-Borchert theorem are kind of interesting. Any questions about this proof for coding? All right, good. So let's try to prove these inequalities that were our upper and lower bounds for the number of unlabeled trees. So let's return to this theorem that I was claiming. So let me name this number, T of n. Let me just call that the number of unlabeled trees on n vertices. All right. And then what we were claiming is that it has these 2 inequalities. It's bounded above by 4 to the n minus 1, and bounded below by n to the n minus 2 divided by n factorial. And then we'll do some analysis on that and show ourselves that that's greater than 2 to the n, but we'll do a Stirling approximation, that kind of thing. Okay, so there's 2 inequalities here, 1 and 2, and they're kind of different the way you do the analysis. And this is sort of typical when you have some interesting combinatorial objects and you're trying to do the asymptotics. Often the methods for producing lower bounds and upper bounds are quite different from each other. So let's do them in that order, 1, 2. And the way I'll convince you of 1 is going to relate to the Cayley-Borchert theorem. So to show 1, let's show this. I'm going to convince you that n factorial times Tn is greater than or equal to n to the n minus 2. All right. Notice what is 1 saying? Let me emphasize what the assertion is, right? That's the assertion in green, and I'm claiming that that assertion is the same as this green assertion. Because all I did is just clear the denominator. I multiplied both sides in this inequality right here, number 1, by n factorial, and I put the t over on the left on this side, and I put the n to the n minus 2 on the right. But I was multiplying by something positive. It's not that I reversed the inequality, it's just I chose to write somebody on the left versus writing it on the right. Okay, so, and the way I'm going to show you this green thing, this assertion here is, this is the number of n factorial, right, is our number of linear orderings of 1 through n, or let me write it this way, number of permutations of 1 through n. And that's the number of unlabeled trees on n vertices. And n to the n minus 2 by the Cayley-Borchert theorem is the number of labeled trees. On 1 through n. All right, that's our Cayley-Borchert. Okay, so instead, I'm going to try to convince you of this, that this set, the size of this set times the size of this set is at least as large as that one. And what I'm going to do is just come up with a map from the Cartesian product of this set and this set, something that has size the left-hand side. I'm going to show you has a surjective map to the set that's counted on the right. So what am I going to do? Via a surjective onto, right? That's what surjective means, an onto map from pairs. Okay, so this is the Cartesian product where I take a permutation, sigma, and a t, a tree, sigma, a permutation of 1 through n, and t, an unlabeled tree, on n vertices, and I just produce a labeled tree. T prime on n vertices, well, on the vertex at 1 through n. Right, so the key word here is surjective. This set right here, whoops, of all these ordered pairs, so I have a permutation and a tree, its cardinality is this number times this number, right? It's what's called a Cartesian product. You just take all ordered pairs from one set and the other, and by multiplication principle, it's got this size. So if there's a surjective map from this set to that set, then this number must be greater than or equal to that number. So let me illustrate this map. It's quite simple, right? Suppose I take, I don't know, sigma is, well, let me draw a tree for you. Let's take n equals 4. Let me draw a tree. Actually, let me draw the tree with some labels that aren't the numbers 1 through 4. Let me just say A, B, C, D. So I've got 4 labels. And I'm just going to think of, I plunk down the A, B, C, D, and I just pick some, I don't know, some random permutation, 2, 3, 1, 4. And I send this pair of sigma and t, whoops. Gosh, kind of messy. Sigma and t, I'm just going to send it to the tree in which I've labeled the A by the 2, the B by the 3, the C by the 1, and D by 4. Okay? And let me do another one, like sigma prime might be an entirely different permutation. You know, A, B, C, D goes to, I don't know, 4, 1, 3, 2. Same tree T, it's still supposed to be just this unlabeled tree, but I'm just giving you a name for the locations of its nodes so I know where to put the things in the permutation sigma. And I'm going to send it to, let's see, so the A is going to 4, the B is going to 1, the C is going to 3, and the D is going to 2. Okay. Now there are many choices of permutation that I could use to label this tree that are going to give me the same result on the right-hand side. The only thing that has to happen is that C gets sent to 1, and I'm going to get a tree that looks exactly like this. It doesn't matter what the A, B, and D do. Same here, like as long as the C goes to 3 in the permutation, I'm going to get this tree, T prime, as a result. These are the trees T prime. So what am I saying? I'm saying this map that I've described, it's not injective. There are many things that map to the same place, but on the other hand, it's definitely surjective. You can see that every tree T prime on the vertices 1 through 4, I'm going to get by picking some permutation and some, you know, unlabeled T here. Everybody okay with that? So that proves that inequality. Let me just say surjective. It is surjective. So inequality proven. It shows this and therefore this. Inequality number 1. Everybody okay? Now, once we have that inequality 1, let's convince ourselves. Once we okay. Once we know that inequality, that Tn is greater than or equal to n to the n minus 2 divided by n factorial. So in the limit, as n goes to infinity, this is approximately n to the n minus 2 divided by, okay, what was n factorial again? Stirling's formula. It's roughly n over e raised to the n, and the roughly is with a square root of 2 pi n in front. And that is, yeah, let's see what happens. There's an n to the n minus, well, first of all, there's an e to the n that goes on top. And then on the bottom, you've got an n squared and also a square root of n. So you get an n to the 5 halves, n to the 2.5, and a square root of 2 pi, I think, constant. And so the way I like to think about this is e to the n, that grows pretty quickly, right? E is almost 3. It's between 2 and 3. So this thing is growing pretty fast. N to the 5 halves, that's, you know, like between n squared and n cubed, it does not grow as quickly. This is really the dominant thing. And so it is essentially growing about like, you know, 2 or 3 to the n. It's in fact greater than or equal to 2 to the n. Certainly in the limit as n goes to infinity, this thing, which is about 2.7 to the n, even though you're dividing by like n squared or n cubed, it's still going to end up being bigger than 2 to the n asymptotically. So that's a rough lower bound, is like 2 to the n. Okay. Now what's less obvious is this upper bound. Before we move on to that upper bound of 4 to the n minus 1, any questions about this analysis of that was our inequality 1 and this asymptotic, you know, lower bound of 2 to the n that we're coming up with? Okay. For the let's let me draw a dividing line. So what did the other one say? We were saying to show Tn is less than or equal to 4 to the n minus 1. What I'm going to do is pick an encoding of an unlabeled tree that is by some information that it's like some code. In fact, it's going to be a sequence of letters up, down, U and D, whose length is going to be, what is it going to be? 2 times n minus 1. And it's going to be enough information to recover the unlabeled tree's structure. If I can do that, that will show you, oh, the number of unlabeled trees is at most the number of these codes, and this number of these codes is going to be, I claim, at most 4 to the n minus 1. So let's do some encoding of an unlabeled tree. So this is a little bit like proof recoding, but it's not quite the same. By a sequence, a sequence of letters down and up. Yeah. Of length 2 times n minus 1. All right, so let me show you how I'm going to do this. So you start with any vertex in your tree, and it doesn't matter which one you pick. Let me think of it as the root vertex. When you pick a vertex in a tree, people often call it a root, picking a root. And then what you do is draw the tree in the plane, on a piece of paper with no crossings. And draw it in such a way that as you move away from the root, you go down the page. Let me show you what I mean. Suppose I began with a tree like this. There's my unlabeled tree. Okay, I just pick an arbitrary vertex to be V0. It doesn't matter who I pick. It could be a leaf. It does not matter. And now what I do is I try to think about picking the graph, the tree up by that vertex V0. I put that thing at the top, and then I just let everything else hang down below it so that I move down the page as I'm moving away from V0. So you see what I did? I just redraw the tree. Okay. And now what you do is you start at V0, and I'm going to show you what you do. Start there at V0, and you kind of walk around the outside of the tree along edges. So you trace the outer boundary of the tree, moving along edges, and you write down D if you went downward along an edge, and you write down U if you went up along that edge. So what am I going to do? I'm going to go that way. I went down. That way, I went down. Actually, I'm sorry. Let me do it all in one motion, and then I'll draw the labels. I go around the tree in the plane and back to V. Does everybody see what I did? Let me put some arrows to indicate how I traverse the tree here, the boundary. Okay. And now the point is, as I went around the tree, I'm actually going to pass every single edge in the tree twice. And I'm going to, sometime it's going to be passing it on one side going down. And then the next time I see it, I'm going to be coming back, say going up, or I might go first up and then down. It depends. All right, so let's write down the sequence of downs and ups. Here I went along an edge down, other edge I went down, then along that same edge I went up, and I went down, up, down, down, up, down, up, down, up, up. And in fact, I think I said it wrong. Every single edge that you're going to visit in the tree, you're going to visit it first going down, and then you're going to visit going up. I think you never end up visiting it, in the opposite order, up, down. So
could we revise this? So like, can we make it a little bit stronger by saying, because by taking advantage of the fact the number of downs is equal to the number of ups?
We could, yeah. So in fact, it's not just true that we're going to get a length of downs and ups that is of length 2 times n minus 1. In fact, as you say, there's going to be exactly n minus 1 downs, n minus 1 ups. So the upper bound we're going to get is actually 2 times n minus 1, choose n minus 1. But asymptotically, that's still about 4 to the n if you use Stirling's formula. If all we care about is like some number to the n, it's not much stronger as a bound. That's why I'm not bothering to be more precise there. But you're right, that actually is a little less loose upper estimate. Okay, so what do? You draw it in the plane. Now you traverse the boundary, the outer boundary. From V0, returning to V0. Writing D and up as you go down and up edges. By the way, this traversal is sometimes called like a depth first search of the tree, but let's not worry about it. So let me do this on the next page, just to write down the downs and ups. Actually, no, we can do this on this page. We've got space here. So what happened? I write down, down, up, down, up, down, down, up, down. Ah, I thought I had enough space. Let's try this again. Give myself a little more space. Okay, where was I? I did down, down, up, down, up, down, down, up, down. Yeah, so I still need to do up, down, up, up. And the claim is that the length of this is 2 times n minus 1, because it's 2 times the number of edges in the tree, and the tree had n vertices. And let's make sure we believe this. 1, 2, 3, 4, 5, 6, 7, 8 vertices. So the claim is that this should have been length 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Darn, I missed. Where did I miss a D and a U? Oh no. D, D, U, D. Oh, this is supposed to be U, U right there. I missed a U. U, U. All right, so where was that? D, D, U, D, U, U. D, D, right there. I'm supposed to have another U. Okay, sorry. Got a little bit small on me. But the point is that once you have this sequence, you can recover the tree. So let's think about how we recover the tree from that sequence. So I'm just going to draw that same sequence: D, D, U, D, U, U, D, D, U, D, U, D, U, U. All right. Can we do it? The claim is I'm supposed to start at some, vertex V naught. And this is telling me I'm supposed to go down, down, then up, then down, then up. Okay, sorry, I have to keep track where I did down, down, up, down, up. That got me to here. Then up, then down, down, then up, then down. Sorry, down is not looking very down, is it? Then up, then down, then up, up. Oh my gosh. I don't know if you believe that, but there's little vertices that we were visiting in between here. And the claim is that the structure of this tree is the same as the one we started with. What did our tree that we started with look like? This one. All right, let me number these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have to think about this. This really does reconstruct that tree together with that choice of V naught, but we don't care. The point is, it did give us the correct unlabeled trees structure encoded in this sequence. So the number of such sequences is greater than or equal to the number of trees. All right, let me put this up here. Oh, sorry, what was I writing? I was going to say it's 2 to the 2 times n minus 1, but that's 4 to the n minus 1. And it's, in fact, yeah, less than or equal to 2 times n minus 1, choose n minus, excuse me, 2 times n minus 1, choose n minus 1, as William was saying. But this thing is asymptotically via Stirling also something like 4 to the n or 4 to the n. I can't remember, something like that. You can check what the Stirling approximation gives you. Okay. All right. Good. So there we have it. We've gotten a rough sense of how quickly the unlabeled trees grow as n gets large. We have an exact sense of how many labeled trees on n vertices there are as the n grows. And so where we're going to head next is some ways to count trees inside of a particular graph, where you don't just allow your arbitrary edges, but you say, okay, I've got certain edges in my graph or multi-graph specified, excuse me, and if it's a connected graph, ask how many different spanning trees there are inside of it. So this is actually something that one of your homework problems alludes to it, but the book doesn't develop any theory for it. So I'll teach you a little bit of that theory because it's rather fun. Any questions before we turn off recording and switch into office hour? Sorry, Jack asked a question. You have one more D than you. Did you say there would be the same number? I did. How old was that question, Jack? I just noticed it now. Old, okay, sorry. And that was because I had my typo in the way I did the thing. Yeah, there should be the same number because every edge, first you visit it going down and then you'll visit it again going up. So they should be the same. Yeah, questions? Okay, recording's going off.